so that system is working, designers have to leave timing margins for voltage. So this is PVT variations. So even if your final silicon is designed typical, is manufactured on a typical lot, you know that you've already left margins for slow lot. Am I right? Because you did the STA across entire lots, the design is same. There could be extra margins that are left for slow lot for the setup time thing, and extra margins left for fast lot for the hold thing. So designers end up using lots of or leaving lots of margins so that the entire PVT range and data dependency or tool inaccuracies are well taken care of. So what happens, even if your manufactured silicon could probably operate at 600 megahertz, because you had designed for a slow lot, what happens, you had to design the system only at 450 megahertz. The system cannot operate faster than 450. That's what the challenge is. Are you able to see this? Any questions on this part?
So to correct this type of thing, we studied that adaptive voltage scaling, we can do something like that.
Adaptive voltage scaling was for different loads. Different loads means different operational loads. But I'm over here now talking only of, let us say, sign off at 1.1 volt.
Okay, so we cannot change the voltage. Yes.
If I'm signing off at 1.1 volt, then I have lost the frequency there. Am I right?
Yes, sir.
At 1.1, I'm saying don't operate faster than 450 megahertz, whereas the silicon that was manufactured could actually have much higher throughput.
Yes.
So I'm losing for all, in an overall distribution, lots which are considered slow could only be 20% of the total lots. But because of those 20%, the remaining 80% are also operating slow, are not able to give the maximum frequency at which they could operate. So the alternative is that you say that, okay, we'll run faster. We'll run faster for everyone. Now, only if there are systems which are failing, only if there is a failure, we will slow down the frequency. So then only in those 20% lots which were slow, you are slowing down the frequency. The remaining you're operating at 600 megahertz. But how do you know that there is going to be a failure at 600 megahertz? So for this, you use two schemes, Canary and Razor. So do you know what canaries are?
So for the STA, we are taking the slow PVT corners.
Yes.
That is the challenge you're mentioning.
Yeah.
But though I could be operating, though my device could be manufactured at different FF or typical corner too.
Yeah.
Okay.
Sir, this is kind of categorization that you are doing, like we were talking in the first class.
Binning.
Binning.
Yeah. So no, abhi main binning ki baat nahi karunga Gandhi. You are able to go in the right direction. What I'm saying is that my system could operate at a higher frequency, but I have constrained it because of my sign-off voltage. How can I remove those constraints? So I say, okay, my system will generate an error signal as soon as there is a failure. Whenever there is a failure, I will reduce the voltage or I will reduce the frequency of operation. So this could be used in adaptive systems also, where if I say that I have a system which is operating at say 500 megahertz, you designed the system and you said, okay, slow lot works at 450 megahertz at 1.1 volt. Now your system was designed as typical, so it could actually operate at 600 megahertz. You wanted to use DVFS. DVFS, yaad hai? We discussed DVFS some time back. What is DVFS?
Yes, sir. We dynamically scale the voltage and frequency
depending on the less load on the processor. We said we will reduce the voltage and we will reduce the frequency. So I want to do DVFS. So I want to reduce from 1.1 volts to, let us say, 1.0 volts. As I do that, I may continue to operate at 450 megahertz only. And I may find that even at 1.0 volt, my system is operational at 450 megahertz simply because it was designed on typical. Can it happen?
Yes, sir. Yes.
So I do not, I continue with the same high throughput for as long as possible, even though my voltage has lowered, so my power consumption has reduced. I'm giving you different kind of use cases where if I could generate an error signal to tell that, oh, now my frequency needs to be reduced, I can start to gain more from the system. Are you able to see this? These examples, are you able to understand these examples?
Yes.
If I'm
Sir,
able to reduce, okay.
Also, it looks like we just want to raise a flag whenever there is a failure in terms of
Yes.
timing, and I will stop scaling them.
Yes, I will start to reduce the frequency of operation then, or I will stop further voltage lowering then.
Okay.
Raghav?
I mean, voltage lowering is not considered here, right?
I just give an example of voltage lowering also, na?
So, but earlier you said na ki we are
I gave two different examples, Raghav.
okay.
One example was where I said that, okay, even at 1.1, I could operate at 600 megahertz. I will operate only those dies which give an error at 450, others I will operate at 600. That was one example. Then I said another use case could be that, okay, 450 megahertz is the speed that I need at 1.1, no problems. But I want to reduce power. So what do? I reduce the voltage of operation until I see a failure. So instead of 1.1, on a typical lot, I will operate at 1.0. Or until I see an error. So this is called as adaptive voltage scaling. Frequency has not scaled, but voltage has scaled so that I could recover leakage. And having such canaries or razors in my circuit can help me generate these error flags. So what is a canary? I come back to my question. What is a canary? How many of you know? No one knows a canary?
Sir, dictionary says it is a bird.
Sorry? It's a
Sir, it is
bird.
a bird.
Yeah, so canary is a very small bird. It's a very sweet musical sound. So, you know, when miners would go into coal mines, they would take canaries along with them. These canaries would entertain them throughout the day. They would just chirp their song along and they would entertain them throughout the day. But entertainment was not the only reason of taking canaries with them into those coal mines. See, there is the coal mines, there is a very big risk. The risk is that there could be a fire due to which carbon monoxide levels can increase and all the people in the mine can get asphyxiated and die. Hai na? So they took canaries along, canaries would sing along and they would entertain them. But if by chance carbon monoxide levels in the mine would increase, canaries are very small, delicate birds. They die as soon as carbon monoxide levels increase. They're very sensitive to carbon monoxide. So as soon as the canary would die, the song would stop. And everyone knows there is a risk of asphyxiation, they would just evacuate the mine. So what is a canary circuit then?
Sir, is it some kind of fuse?
Some kind of
Fuse.
fuse. Okay. So canaries are circuits which are more sensitive than your actual circuit. So if your actual circuit has a timing slack at time of sign off, if it has a margin of, let us say, 100 picosecond, the canary circuit that you will put in your system will have a margin of only 50 picosecond. So if somehow delays increase because you lowered the voltages, because as you lower the voltage, delays would increase, the margins on the canary circuits would reduce or become zero or become negative before margins on actual circuits. So canaries would fail first. As soon as canary fails, you have the error signal and you can stop further lowering. Are you able to see this?
Yes, sir.
Now, then what is Razor?
It's a rate. It sounds like it will cut apart all the scaling system.
So Razor stands for razor edge, very sharp. See, with Canary, what happens? I said my minimum margin was 100 picoseconds. So I designed my Canary with a margin of 50 picoseconds. What this also means is that for all the paths, even for those paths for which margin was 500 picoseconds, my Canary would fail much earlier. It could happen that my how do I say? It could happen that my critical path, which is active as of now, had a margin of 500 picoseconds. So even at lower voltage, it would not have failed. I'm suppose using only an adder, not a multiplier. So adder can actually operate at a lower voltage without any failure. But my canary, because it was designed for the multiplier, canary failed. Can it happen? So now I'm not able to gain further power, recover further power. So that is when Razor comes in. Razor says that, okay, I will check your exact circuit and I will compare it with the delayed version of my signal. So only the delayed version is different from the actual one which I have latched, I will say there is an error. If the delayed is same, that means there is no error. It's something like what we were discussing earlier in the day, where we said that after contamination delay, the signal is stable. Yes, that particular signal is stable, but the entire signal output may not be stable. So what we are looking is, when we're talking about Razor, is for every shift resistor, for example, we could have a sensor which says that, okay, are the contents of my Razor when I sampled different from the contents, say 100 picoseconds later? If the contents are different, you say, oh, I have sampled something wrong. Otherwise, you say, wow, I sampled everything correctly. Let's move ahead and do this next set of calculations. You have a question?
So are these two doing the same thing? Like
They are generating an error. In that sense, they are doing the same thing. But at the time of designing, the philosophy is very different. For Canary, you are making the slowest possible circuit. For Razor, you're not doing any such circuit redesign. You're simply sampling the circuit again.
okay, and both these are to basically see what is the edge of my performances, like how fast
Yes.
it can go.
So so canaries are not much in fat today because the kind of margins that you have to leave, the gains that you can get from canary are not significant. But Razor is something on which some sufficient amount of research is continuing to happen to make it, proactively available in industrial designs. So if you would want to, know more about it, you will see that there are papers on Razor, improvement in the original Razor idea and all that, even in very recent years. In fact, our group has also published some papers on Razor over the past some years. A few people are working on Razor techniques even now in this semester. Your seniors are working on Razor techniques. So this is an area of active research, adaptive sequencing, and if you're interested, you could probably do some projects in the next year. Gagandeep?
Sir, this razor, it would be complex, right? Otherwise, I could build a razor by using some buffers and
That is
XOR
why
bits.
research is happening now, Gagandeep. That is what we want to simplify.
Can you just give a brief of what sort of circuits do we use in this razor?
So razors simply or usually require redesign of a flop so that there is an extra latch in the flop. The extra latch samples at after some delay only. So the data has come, the output will be latched twice, once on the clock edge, once on a delayed clock edge. If both the data are same, you say great. If they are different, then you say there's an error. So it's a much bigger flop that we have when we use razor.
Yes.
Okay.
In this razor thing, the sampling, can I, for example, just for the simple understanding, can I say that the different intervals, the M&M sampling, that could be the difference between like between the contamination and the propagation delay?
How you define that margin, that is not really
Okay.
dependent on contamination and propagation. That's a designer's
Okay.
prerogative. What kind of margin you want to leave, that is what defines that. Okay.
Okay. So, but like in physical implementation, that is the kind of thing that is
I can't comment on that. There is no such rule.
okay. But ultimately, it is because that sampling. Ultimately, I'm saying that when my data would be stable.
Yes.
At
In
the
propagation
earliest.
delay.
At the earliest, when my data will be stable.
So I'm talking of propagation delay because
Yes.
data is stable.
Yes, sir. Okay, but they can
Contamination
be
delay still doesn't come into picture.
okay. But they could be different variation in that propagation delay itself.
Yeah.
Okay.
Okay.
Sir,
Yes, Debjit.
sir, I want to ask about this razor thing. Sir, you told the data in the clock cycle and the skewed clock cycle will be evaluated, and then some kind of XOR thing would be done to check. I think is it something like that?
Yes.
And one more thing I wanted to ask that there are some universal time constraints that are related to every latches and flip flops. Like you said, the setup should not be 5% of the minimum. So these, and also let's say the pulse width, these mainly depend upon the drive strength of our means internal circuits of the latch and flip flop. And the